lot of new definitions, but there's something that is not new. You saw it already during the high school, the kinetic theory of gases, and for sure you will have to apply it. PV equal nRT. This is also important, and also the expansion, adiabatic expansion, and the specific heats. So these are important things that you should at least remember. Now today we talk about the entropy. Your time looking the equivalence of the word entropy in Vietnamese, because it does not exist. Entropy, but I think you might already heard about this word, even before you learn it. The famous entropy, what is it? We are going to find out today in the last session for the thermodynamics. So for of this, bạn nào còn chưa tắt mic tắt hộ tôi nhé. For the outcomes of this part, we will understand the second law of thermodynamics. We can define and calculate the entropy of the system. And we can apply the second law. So there are two famous applications of the second law. We talk about the heat engines, or in short, the engines only. Actually, when we say an engine, this is a heat engine, okay? And the refrigerator. So inside of every house, you should have, I suppose, one refrigerator, right? But you know that the air conditioner is also working with the principle of a refrigerator. The difference is just the gas, okay? So in the refrigerator, you may use a different cooling gas than what we find in an air conditioner. That's all. Good. So is it clear for the outcomes? Now we can start. Firstly, we will talk about the entropy. So what you see is that around us, we see a lot of irreversible process. So I mean processes that once happened cannot return to the initial state anymore. So in the previous part, we saw a lot of reversible process, right? For example, a gas. For the initial state of the gas, we can define as the temperature, the volume, and the pressure of the gas. So, for example, if we call an initial state Pi, Vi, Pi, after several times, in the initial state, so Pi, Vi, Fi once again. So this is a simple system. Bạn nào vẫn còn mic tắt ở thôi kìa. A simple system where we consider a reversible process. So processes that after several changes can restore to the initial state. An open system can still have reversible processes, right? But around us, in reality, we have a lot of reversible processes. So processes that once it happened cannot be restored to the initial state. Here, for example, I have very simple examples. When we drop an egg onto a floor, can we restore the egg to the initial state? Yeah, we know that we cannot, right? Or when we bake a pizza, but there's no way we put the pizza already cooked into the powder, into the ingredients again, right? Once already cooked. Or when we drive a car and we hit a lamp post, there's no way we can put our car in the initial state before the accident happened. We know it, but why? Why we cannot restore it? Why these processes only go in one way? This is the question we will try to answer today. We understand the meaning. Why by institution, we know that it should happen in this direction, right? And not that direction. By institution, we know it, how to explain it. So that's one way, for us to explain is that we use the notion of entropy. If we understand what entropy is, we can use the notion of entropy to explain for the direction of irreversible processes. So that's why we say that the idea of entropy will provide a mathematical way, a mathematical way to encode the intuitive notion of which processes are impossible, of what direction an irreversible process should follow. We try to explain what we intuitively notice, in a mathematical way. Good. So entropy, what is it? If you look at the internet, you type Google. So 20 years ago, our generation, we didn't have much of the internet. We had to refer to the book. But even in the Vietnamese book, we say that the entropy is a matter of the disorder or of a randomness of a system. This definition still holds even until now, but a lot of people misunderstand the word of disorder or randomness. Okay, here I will try to explain as clear as possible what is the disorder that the entropy is talking about. Yeah. This term was actually first stated in 1865 by Clausius, and the meaning was initiated from the Greek language with an equal to in. Entropy is actually a turning point. So this is the point where we turn something. Okay, this is a rough idea of entropy. So in a turning point, we try to consider a change. Yeah, the moment where something is changed, we turn something into a different thing, an entropy. And this concept was developed initially to respond to the observation that a certain amount of energy released from the combustion reactions is always lost. So at the beginning, when I talk about Cardinal, so you should remember, right? Cardinal, he was the one who first started the concept of the engine, the entropy change inside of the engine. And at that moment, scientists also try to explain why the energy is always lost from the combustion reactions. Maybe due to the dissipation or the friction. Why all of energy cannot be transformed into useful work. So they try to explain it, and then the term entropy appeared as a way to try to explain. Good. That's why we will learn two ways to define the entropy of a system. The first way is to use the microscopic approach. Okay, microscopic approach. So this is the way where we will count the ways in which the atoms or molecules that make up the system can be arranged. The way in which the atoms or molecules that make up the system can be arranged. So this is one way we define the entropy of our system. The second way is to use a macroscopic approach, where we define the entropy in terms of the system temperature and energy the system gains or loses. So this is the way that has a direct link with what I just said, the entropy change in a heat engine or in a refrigerator, for example. Okay, and in the second way, we will study more closely in the framework of this year. But we still have to know the first approach, the microscopic approach, to define our entropy. Okay, two ways, two equivalent ways to define entropy: the microscopic approach So we count the way in which the atoms or molecules that make up the system can be arranged. The second way, the macroscopic approach, where we explain the entropy in terms of the temperatures and the energy of the system. The energy as heat of the system gains or loses, it will give us a way to define the entropy of our system. Good. Now we go a little bit deeper into the microscopic approach. Firstly, I have an example. You can see here 2 rooms. So one room, the first room here, if you see the mouse, please follow it. We say that the entropy is the measure of the disorder of the system, right? Disorder of the system. But here I have 2 rooms. One room, you can see this one is quite ordered, right? We say this one is ordered. Trong tiếng Việt chúng ta nói là phòng đầu tiên nó ngăn nắp, nó gọn gàng hơn đó. Không biết bạn Trương Hiền Anh có thấy thế không? Or maybe you see that the second room, like this way, is more ordered. I'm not sure. Maybe it's more similar to your room. I'm not sure. But in a normal way, okay, if we just look at it, we look at 2 rooms. For me, I will see that the first one is more ordered than this one. This one is very messy, very disordered. Okay. Đó, nếu như chúng ta nhìn vào hình ảnh, chúng ta sẽ thấy là cái phòng đầu tiên này nó rất là ngăn nắp gọn gàng, trong cái phòng thứ hai thì nó không. Nó messy này, nó rất là bừa bộn, đúng không ạ? Hy vọng là bạn Trương Hiền Anh là đồng ý với tôi cái khoản này. But this one is very different than the word disorder that the entropy gives us. Very different, okay? Because something that is messy doesn't mean that it has more entropy. Even if we look at the moon or the sun, people might say that, okay, the moon is less messy than the sun, so it has less entropy than the sun. But how to prove it? How to prove it? It's a different way. We cannot just look at a system, and we, intuitively say that this one has more entropy than the other one. We have to measure it, right? Here, we say that the disorder of entropy, is of the number of states that a system can take on. Of a system, the number of states that a system can take on. So you understand until here? Let me take an example of 2 systems, very simple systems. One system has 4 atoms, and one system has 8 atoms. So we consider the 2 very simple systems. Good. What do we have? So 4 atoms here are encoded with different colors, okay, and 8 atoms. What do we have? What do we have? Here, for a system of 4 atoms, for sure we will have a fewer possible states than a system having 8 atoms, right? If we change the place, the position of one atom, for example, the yellow one, to this one, yeah, if we put it into another position, to this one, we have a new state. If we put the pink atom into another position, we have another state of this system, right? Then we count to see how many states this system will have. But even this, we know for sure that a system having more atoms, having 8 atoms, will have more possible states, right? Because it has more atoms. Then one atom will have more position to change in this system, right? And because it has more atoms also, it will have more states. Do you agree with me? Yeah, so we say that yeah, this system will have more entropy. Sự bạn Nguyễn Phương Thảo có đây không nhỉ? Sao bạn làm gì mà cây mọc trên đầu ấy nhỉ? Tôi thấy một cái avatar của bạn. So we say that this has more entropy, okay? Because it has more possible states. And we call these states the microscopic states. So this is defined by Boltzmann. So he defined entropy as a matter of the number of possible microscopic states of a system in thermodynamic equilibrium. Okay. A measure of the number of possible microstates of a system in thermodynamic equilibrium. Good. So please remember this definition. Now, we will use the entropy to explain what I just said. Why an irreversible process has a direction. It can only go in this way and not that way. Okay. Why? We consider a system of 6 atoms. Six atoms. And these 6 atoms are confined in a box. Okay. With a good insulation, we consider that this is a closed system. These 6 molecules are identical, so we cannot distinguish them. You understand here? We cannot distinguish. And at any instant, a given molecule, yeah, will be either in maybe the left or in the right of the box. The 2 halves will have the same volume. Okay. So at any instant, we may have a certain number of molecules that are found in the right half or in the left half. And these 2 halves are exactly identical. So what we have that the probability of finding the molecules in either the right or the left is the same. So the molecule, each molecule will have the same probability, yeah, of being found in either half. Good. Mỗi cái phân tử của chúng ta thì sẽ có cái xác suất được tìm thấy ở một trong hai nửa là như nhau, đúng không ạ? Bởi vì nó giống hệt nhau, hai nửa nó cũng giống hệt nhau. Is it clear until here? If yes, okay, I continue. Then we can define, no, we can count the possible configurations of these 6 molecules, right? The configurations. For example, here, the configuration number 1 is the configuration where all of the 6 molecules will be found, yeah, maybe in the left, yeah, in the left of the box. So the number 1 and the number 7 is similar. So the situation where 6 molecules will be found all in the right half or all in the left half. Okay, you see the 6, 0. Similarly, we define all the configurations. For example, the 5 and 1, so 5 molecules in one half, 1 in one half, and so on. And here we have the situation 4, so half molecules will be found in one half, and other half will have also half of the number of molecules. Good. We continue. So we call these different arrangements the molecules microstates. Okay. Okay. So each microstate can be found in either 1 to 7 configurations like this. Then what do we count? We have to calculate how many arrangements do we have in our system. Here we will have to use a little bit of mathematics. So we suppose that n is the number. We suppose that the n molecules, the number of molecules that we have, are distributed with n1 molecules in one half of the box and n2 in the other half. Of course, we have n1 plus n2 equal the big N, the number of molecules. So we can calculate the total number of ways in which we can select all 6 molecules. And this is the number, that we can calculate in this way. We can use a little bit of mathematics. So this is the factorial of 6. When we say 1 times 2, 3, 4, 6, here we will have the factorial of 6. So this factorial 6 here equal to 720. So this is the total number of ways in which we can select all 6 molecules. Okay. But what we have that our molecules are distinguishable. Indistinguishable. So these arrangements, the numbers 720 here, so these are not all different. So we will have a lot of identical arrangements, right? So we will have to eliminate the identical arrangements because these are the same. So we cannot use the factorial 6 to calculate the number of microstates because we know that there are a lot of arrangements who are identical, so we cannot count them twice. Yeah. Đúng không ạ? Nếu như mà ta dùng công thức này, công thức toán này, thì chúng ta biết là sẽ có rất nhiều cái sắp xếp của chúng ta. Thực chất nó chỉ là một thôi. Bởi vì các cái molecule, các cái phân tử của chúng ta là không phân biệt được. Thì chúng ta không thể tính một cái arrangement 2 lần được, đúng không ạ? Chúng ta phải có một cái cách để chúng ta loại bỏ nó. Then we need to use once again a little bit of mathematics, statistics, and probability. Maybe you do not learn it yet. You will have to learn it during the second way. That's why I just introduce it here. I will not ask you to calculate or to understand it, but you have to accept it. To get the number of different arrangements, we have a way to calculate, and this is the formula. We have a more formula to calculate the multiplicity of configuration. So this is also the number of microstates that correspond to a given configuration. So this is the formula, okay? To calculate the multiplicity of configuration, which is exactly the number of microstates of our system of 6 molecules. So if we apply this formula, what do we have? The factorial of 6 divided by factorial of 6 times the factorial of 0. This is for the configuration 1. We have 1 here. Similarly, if we apply this for the configuration 2, we will have 6 number of microstates. I mean the number of different arrangements for our molecules. If we continue, we will see, yeah, different number here. And if we look at our configuration, where half of our molecules will be present in one half, and half of our molecules will be found in the other half of our box, it will have the higher number of microstates. Yeah, the highest number of microstates. Good. And we will have in final a total number of microstates for our system of 6. Remember, our system has only 6 microstates. Then we will have a number of 64 microstates for our system of 6 molecules. Good. Nhiều bạn mà để cam đây mà tôi chả thấy mặt đâu nhỉ. Trần Hữu Trí cũng không thấy. Quỳnh Trang thì mình thấy mỗi cái mũ. Okay. So for example, how do we understand it? For example, if we consider the configuration 4, and this is also the most probable configuration, as I just explained, it will have a probability of 31.3%. It means that this system is in configuration 4 for 31.3% of the time. And this is the most probable configuration. Yeah. Like I said, this configuration corresponds to the situation that the molecules are evenly divided. Yeah, evenly divided between the two halves of the box. Yeah. And this is also the thermal equilibrium that we expect. Right? And if we look at the configurations 1 and 7, so all the molecules are in one half of the box. So this is the least probable configuration with a probability of only 1.6% for our system of 6 molecules. Remember? Các bạn đào Minh Anh là cái mặt thành cái bánh mì là như thế nào nhỉ? Thánh nhỉ? Chỉnh lại cho bình thường đi, không các bạn dai các bạn lại muốn ăn, đang đói cứ xông vào ăn thôi.
Tại background của nhà con đang bận, đang vừa vội thế là con
rồi chuyển background đi em ơi. Okay. So we see with our system of only 6 molecules, the probability of finding all 6 molecules in one half of the box is already very, very small. You see, only a little bit more than 1%. Yeah. Then what will happen if we consider a bigger number of molecules? Okay, if for example we consider one more, yeah, of the 6 times 10 power of 23 atoms, so what will happen? We will see that the configuration in which the molecules are divided equally between the two halves. Yeah, we take the most, right? Why? The probability for the configuration where we can find all molecules in one half, yeah, are very, very close to 0. Yeah, exactly very close to 0 if we consider a large values of molecules. Good. And one more is still already very small. Around us, we have a lot of systems, yeah, with a lot of moles inside. Good. So in this way, we will see that we know the way, right? A system, a process, an irreversible process should go. So it should go in the configurations, yeah, having the highest probability, and cannot go to a configuration having very small probability, even close to 0. If we reconsider our example of an egg dropped onto the floor, because, yeah, the egg will be broken down. It's the configurations that having the most probability to happen. That for sure, our egg, yeah, our process will go into this way and not that way. Yeah, not in the way that the egg will be restored. Yeah, after being dropped out, because the probability for that to happen are mostly 0. So we know that a system will have to choose the configurations that have the highest probability to happen. Mũ nồi đẹp đây Duyên ạ. Chọn cái ý đi. Good. And Boltzmann once again in 1877 already derived a relationship between the entropy and the multiplicity. Okay, he developed a way to calculate the entropy of the system, to try to relate the definition of entropy with the number of microstates. And this is this one, S equal K ln W. Here we have K is the Boltzmann constant, okay? And ln W is the natural logarithm of the multiplicity. So if we apply this formula for our 7 configurations, we will see here the value of entropy of the configuration 4 is still the highest. Okay, it's still the highest. So the configuration having the highest probability to happen, the system will be in this configuration most of the time. We also have the highest entropy. So in this way, the entropy is really a matter of the number of microstates. So it will, the entropy will have a meaning to say that, okay, so this is the configuration that the system will take the most and not this one. If the entropy equals 0, we know mostly for sure that this configuration cannot be happen. If the configuration is the highest, has the highest entropy, we know that this configuration will be taken the most for this system. So in this way, the entropy can be used to define the way the state of the system will go. So the system will have to go in this way and not that way, just by looking at the number, the value of entropy. Okay, so this is the way we define the entropy using the microscopic perspective, and we can also use the entropy to explain the direction of an irreversible process. So this process, this go in this way and not that way. Do you understand until here? Any questions so far?
May I?
Yes.
What is
Cannot hear.
what is the units of entropy?
I know for sure that no one can hear you. Maybe you type so then I can answer, because your microphone is terrible. So if you have questions, please type here. I propose also that we take a break. Please use the chat box. You use the chat box. The unit of entropy you will see. Actually, it's joule per Kelvin, but you will see in the next part. Okay, joule per Kelvin. So I propose that we take a break 10 minutes, then we will start again. the lesson. Good. Is everyone here? Okay. Let me restart, I mean. We just finished the first way to define our entropy, the macroscopic approach. I hope you understand right now. So what is entropy, right? And then the way we use entropy to explain irreversible process. So we know that why an irreversible process should go in this way and not that way. Yeah, it has a direction, so it should follow. And we will go to the second way. This is an exercise I will just show you. I will not ask you to do because the number is very big. So we will see it together before we go to the second part. Now we have a system of not 6 atoms anymore. We have 100 atoms or molecules. 100, okay? It's still very small. It's still nothing. But if we look at the situation, I call the situation half-half. So 50 molecules are found in one half and 50 are found in the other half. So we consider this situation. And we will compare the multiplicity of this configuration with the configuration that 100 molecules are found in one half and the other half have 0 molecule. So if we calculate the configuration half-half, I call it, we will have a very big multiplicity. So the number of microstates is this one. But for the configuration of 100 0, so 100% of the molecules are found in one half, the multiplicity is only 1. So you see the difference. You see the difference. So this is 10 power 29 times bigger than this. So you see here. So this contribution, is more likely than this configuration, than this distribution. Okay. This distribution is more likely than this distribution by the factor of 10 power 29. So very, very big. That's why in reality, we never see this configuration for our big system. Yeah, our system in reality is too big. It's not only 100 molecules. Yeah. It's not one more, but it's much, much bigger. Good. So this is the first way. Now we go to the second way, and this is also the heart of this session. And in the framework of the first year, we will also pay more attention to this approach, the macroscopic approach, for us to apply it in our gas system and later on in some applications. Good. Now, in this approach, we define the entropy in terms of the system temperature and energy the system gain or loses. In this way, we understand the entropy as a measure of the system's thermal energy per unit temperature that is unavailable for doing useful work. Okay. A thermal energy per unit temperature, yeah, of the system that is unavailable for doing useful work. Right? You understand? Remember, at the beginning, I told that the entropy was developed firstly to explain why there are always energy lost due to the friction, for example, dissipation, for example, and cannot be turned into work because the work is obtained from ordered molecular motion. Okay. And if we are able to measure the energy per unit temperature that is unavailable for doing work, we also measure the molecular disorder, or another word, the randomness of the system. So this corresponds to the friction, to the dissipation, and so on. The energy that is unavailable for doing work. And in this approach, we pay attention on the change in entropy. So we should know when the system changes from one state to another, what will be the change in entropy of the system. Then we can define this change in entropy in this way. So the change in entropy equals the integral from I to F of differential heat, divided by the temperature. So here the differential heat is very small change of heat. So you understand, right? Per unit of temperature here. Then we sum every small change of that heat per temperature. We will have the change in entropy. Good. So this is the way we define our entropy. Please remember this formula. Is it okay? We continue. So what we see here is that the entropy change, will depend on two things: on the heat of the system and also on the temperature at which the transfer of heat takes place. Okay, it depends on the heat transferred from or to the system, but also on the temperature at which the transfer takes place. So it depends on two things. I'm sorry, I'm having a phone call. Good. If the temperature change is quite small relative to the temperature before and after the process, we can just write the change in entropy in this way. So the change in entropy is just the heat over the average temperature. And here, after a lot of experiments, we prove empirically that entropy is the state property or a state function. Actually, a state property is also called a state function. So the entropy depends only on those states and not all on the way the system went from one state to the other. Okay, so it really depends only on the initial state and the final state, and not at all on the way the system went from one state to the other. Good. So here, in this way, we can find a way to calculate the entropy for an irreversible process. Okay, I will explain it in the next slides, but now you accept that to find the entropy change for an irreversible process, we replace that process with any reversible process that connects the same initial and final states. So you remember, for example, an irreversible process, which is the free expansion, right? Once we release the Stock between the two halves of the container, the gas will go from one half to the other, having only the vacuum. So this was the example given to you several times already. Then it cannot be reversible, right? So this is an irreversible process. So to calculate the entropy of this process, so we cannot use this formula because there's no connection between the initial state and the final state. So we cannot use the integral. That's why we need to find an indirect way to calculate it. Những quá trình không nghịch đảo thì các bạn không thể dùng cái công thức entropy này để tính toán một cách trực tiếp được. Ví dụ như là tôi lấy cái chu trình mà giãn nở tự do, đúng không ạ? Khi mà chúng ta mở cái khóa ra đấy thì một bên khí nó sẽ tràn sang bên mà chỉ có chân không, và cái quá trình đó thì tất nhiên là chúng ta không thể nghịch đảo lại được nếu như để tự nhiên như vậy, đúng không? Thế thì nó sẽ không có cái mối liên kết giữa điểm đầu và điểm cuối, thì chúng ta không thể dùng cái integral này được. Đó, về mặt toán học mà nói thì chúng ta không dùng được. Cho nên chúng ta phải tìm một cách tính toán, vẫn dùng các cái công thức này nhưng chúng ta phải tìm một cách tính toán cho một cái chu trình thuận nghịch. Đúng không? Một cái chu trình thuận nghịch mà nó có cùng điểm đầu và điểm cuối với cả cái chu trình không thuận nghịch của chúng ta. Đó, bởi vì chúng ta theo thực nghiệm thì chúng ta nhìn thấy là entropy này nó là một cái state property hoặc là state function, như cách gọi của state property có nghĩa là nó chỉ phụ thuộc vào cái điểm đầu và điểm cuối thôi. Đó, chứ nó không phụ thuộc vào cái cách mà nó đi từ điểm này tới điểm kia. Đó, nó giống như là nội năng đó. Nó giống như, đúng không? Biến thiên nội năng nó cũng chỉ phụ thuộc điểm đầu điểm cuối. Nó giống như pressure, giống như temperature, nó chỉ phụ thuộc vào điểm đầu điểm cuối. Good. Những cái nào hơi khó hiểu thì tôi sẽ giải thích bằng cả hai ngôn ngữ để các bạn, mục đích là các bạn nắm chắc được. Now, we just said that the entropy is a state function. And this, I also said that we can only be deduced by experiments. Okay. However, we can prove that it is really a state function for the special in an important case in which an ideal gas is taken through a reversible process. So we cannot prove it. We can just experimentally observe it for irreversible process, but we can find a mathematical way to prove that the entropy is a state function for reversible processes. Good. Now we consider a reversible process with the ideal gas in equilibrium states. If we apply the first law in the differential form for this reversible process of our gas, we can write it in this form. Then remember, for our ideal gas, if we want to calculate the heat, we will have, okay, the work here, the very small change of the work is P dV. Good. And the change in the internal energy, very small change in the internal energy equal NCV dt, LCV dt. Remember the last session when we worked together, we know it already, right? So delta T equal NCV delta T, right? I hope that you still remember. Hope so. Now, if we apply the ideal gas law, what do we have? Firstly, we divide the temperature in both sides, right? And here we replace the new expression. So P over T will equal NR over V. We apply our first law of ideal gas law. Then we take the integral to have, you see here the formula, our formula to calculate độ minh tú. What is it? Đấy, tôi đang thấy cậu nhìn đi đâu ấy chứ. Tôi kích bạn Minh Tú này ra ngoài nhé. Không điểm danh nhé. Tôi không muốn là mấy bạn mà ngồi đây xong mấy bạn làm cái gì ấy. So we put the integral here to have the expression of the entropy. Trong mấy ngày nữa trước thì lại bảo là thầy ơi cho em xin. Không khó đâu. Phải tập trung đã chứ. Này, xem có học đâu mà lại cứ đòi qua.
Xin lỗi ạ.
Tập trung vào nha, tất cả các bạn. Không đủ đâu, tôi thấy rất nhiều bạn thế đấy. Now, how do we calculate? We have this expression, right? We have this expression. What do we see here? We see here that it only depends on the initial states. So here we have the temperature, initial temperature, the final temperature. We have the initial volume, the final volume, right? And it depends only on the initial state, and the final state. Here we do not specify a specific reversible process, so it should hold for any reversible process. In this way, we already proved that the change in entropy is a state function for reversible processes. And you can also remember this formula for us to apply. Yeah, when we calculate the change in entropy for both reversible and irreversible processes, because for irreversible processes, we still have to find a way, to replace it with a reversible process having the same initial and final state. Good. Now I have an exercise for you to practice and for you also to understand better what I said. Here I have two identical Cooper blocks. So TL and TR here. So the block TL has a temperature of 60 degrees Celsius and block TR has a temperature 20 degrees Celsius. Okay, so these blocks are put inside the box and separated by an insulating shutter, like this one. When we release the shutter, we have an irreversible process. So the temperature from TL having higher temperature will be transferred to TR, right? Having lower temperature. So at the moment, we will have an equilibrium, thermal equilibrium, and the final temperature is 40 degrees Celsius. Now we will need to find the net entropy change of the system of two blocks. How do we do it? I give you 5 minutes. If you have the solution, you can send me to the chat. Có khi tí mời bạn Nguyễn Phương Duyên nhỉ, xem hiểu được tới đâu rồi.
Em đây ạ.
Làm bài thử đi, tí tôi gọi để chữa. Bạn Mai Chi đâu nhỉ? Tôi chỉ thấy camera của bạn trên trần đi.
Em ạ. Tại vì em dùng điện thoại ra nó chữa lên một tên của
Teacher, your mic is
Thấy mỗi cái trần nhà thôi. Okay. No one has the answer. Then to solve it, how do we solve it? But to solve it is easy, but you should understand one way, one thing. I'm sorry. Here. I'm sorry. I'm sorry. So here the calculation is held firstly for a reversible process. Okay, the calculation is the same, but we should say that this one is held for reversible process. So we already replace our irreversible process with a reversible process that holds the same initial and final state. Otherwise, we cannot apply this formula. Okay. The calculation is the same. Here, firstly, we apply the change in entropy for our Cooper block in our left. And here we apply the change in entropy for our block in our right. And the net change in entropy is this one. Actually, it's the sum of the two change in entropy. The thing here is that if we consider the block on your left is a system, okay, and the right is also a system, then we will have an open system. And with an open system, the entropy might be positive or negative. But if we consider a closed system, then the entropy should be always positive or equal zero. This is the problem. So you see here, if I write the minus something here, is that I calculate the entropy for the Cooper block in my left but for an open system. Good. Ở đây tôi giải thích một tí. Cái việc đầu tiên mà tôi nói đó là chúng ta phải thay thế. Cách tính toán thì nó vẫn thế thôi. Nhưng mà chúng ta phải lập luận là chúng ta thay thế cái quá trình không thuận nghịch của chúng ta bằng các cái quá trình thuận nghịch tương đương mà có cùng điểm đầu điểm cuối. Thế thì ở đây thì chúng ta có một cái hệ không thuận nghịch là hai cái block. Đúng không ạ? Thế thì chúng ta có thể tính toán để cho cái quá trình thuận nghịch mà có cùng điểm đầu và điểm cuối. Đó. Thế thì ở đây thì chúng ta có thể consider, chúng ta có thể xem xét cái hệ là hệ mở của cái cục đồng ở bên trái và hệ chỉ có cái cục đồng ở bên phải. Thế thì ở cái cục đồng ở bên trái thì chúng ta có gì? Nếu như mà chúng ta chỉ tính ở cái cục đồng ở bên trái thì nó sẽ có một cái nhiệt lượng đúng không ạ? Nó sẽ có một cái nhiệt lượng ban đầu đúng không ạ? Nó sẽ có một cái nhiệt độ ban đầu. Và chúng ta biết là chúng ta sẽ có cái khả năng để chúng ta khôi phục nó thành một cái nhiệt độ ban đầu đó bằng cách thêm nhiệt, trừ nhiệt đi. Tôi xin lỗi, tôi lại có điện thoại. I'm sorry. Ok, thế thì cái chúng ta tính toán, chúng ta sẽ tính toán là cho cái chu trình thuận nghịch, đúng không ạ? Và chúng ta sẽ tính toán tổng. Đó. Tổng của cái chu trình thuận nghịch này thì nó là bằng 2,4. Và chúng ta biết là cái tổng này, tổng thay đổi của entropy này nó cũng sẽ bằng với cái chu trình không thuận nghịch mà chúng ta vừa mới nói. Đó, chúng ta vừa mới nói. Thế thì như vậy là đây là cái cách tính của chúng ta. Chúng ta không thể nói là chúng ta đang tính cho chu trình không thuận nghịch dù cho kết quả nó là như nhau. Bởi vì theo toán học mà nói thì chúng ta không thể áp dụng các cái công thức này cho một cái chu trình không thuận nghịch. Ok. Đấy là cái giải thích là...
Teacher? So from the beginning, we have two equations to calculate the delta S. So when will we use the one or the two equation?
Actually, from the beginning, you have to explain that we are calculating the change in entropy for the two-step reversible process having the same initial and final state with that of the irreversible process. And from this way, you can calculate that the formula, mathematical formula is still the same, yeah, but the physical meanings is different. And when you find the results for the change in entropy for reversible process, you explain once again that this change in entropy is also equal to the change in entropy of the irreversible process. That's all. So you understand the way we do?
I actually do understand, but what I ask is that we have two equations to calculate the delta S, the shorter one and the longer one. So when will we use the first one or the second one?
It's up to you, and it depends on the hypothesis that you have. For example, here we have the heat, and what is given? We have the C is given. We know the mass. So why do not we use the MC delta T, right?
Okay.
We know that it is MC delta T. So it really depends on what information that you have to calculate. Đúng không ạ? Thì bây giờ các bạn phải có đủ dữ liệu thì các bạn mới biết được là các bạn dùng cái gì chứ. Công thức thì các bạn có rồi, Q bằng MC delta T ở đây nó cho đủ MC, đúng không? Delta T, thế thì các bạn dùng công thức này. Còn nếu mà tùy vào dữ liệu mà đề bài cho nhé. Okay. Here, I have a similar exercise. So now I have 1 mole of nitrogen, which is confined to the left of the container. Here you will see that this is a free expansion. When we open the Corstock, of course, the volume of the gas will double, and there will be a change in entropy. There will be a change. And we know that this process is also irreversible, right? If we consider the whole system here is also reversible, then how to solve this question? Good. So firstly, we will have determined the entropy change for a reversible process that provides the same change in volume. So it will have the same initial and final state, right? And what we know also is that the temperature, the initial and final temperature of this system is constant. For a free expansion, the temperature remains constant, okay? Then we should be able to define our reversible process as an isothermal expansion, having the same initial volume and temperature and the same final volume and temperature. Is it good? Good. Then we calculate as normal. Once we do it. For example, here we have the heat equal nRT ln Vf over Vi. Then we have this one, and so on. And then after that, we will have the change in entropy for the reversible process as this one. This one is for reversible process. Good. And we know that the change for our irreversible process is exactly equal to this one. So you see the calculation is one thing because we use mathematics, but physically, you have to explain that firstly we are calculating for an equivalent reversible process, and we do not calculate the entropy directly for our irreversible process because we cannot. Các bạn hiểu chưa? Đó, vật lý nó khắc toán đó. Good. Now we will go to the second law of thermodynamics, and after that we will go to some applications. For the second law of thermodynamics, what do we have? Now we consider a closed system. Okay, this time we consider a closed system of the thermal reservoir and the ideal gas inside the piston. And this system expands isothermally to simplify our problem. We can easily calculate the entropy change for the gas, which lose the heat. Okay. This one is the entropy change for our gas. Now we can calculate the entropy change for the reservoir, which gains the heat. Good. Then we can write like this. So we have a change, the two changes in entropy. So finally, what do we have? We have the change of the closed system equals 0. Right? Here, this is when we consider a closed system. Reversible process. Reversible process. Previously, we consider the entropy of an irreversible process. So we know that the irreversible process entropy, change in entropy is always positive. Now, when we consider for a closed system, and we know that this system is reversible, right? The gas here is reversible. So it can be restored to the initial volume, initial temperature, initial pressure. So here the change is 0. Then we have the entropy postulate. If a process occurs in a closed system, the entropy of the system increases for irreversible processes and remains constant for reversible processes. It never decreases. So the entropy of the second law of thermodynamics can be written simply in this form. But you remember, once again, it should hold only for closed system. Okay, closed system. In our exercise that I gave you here, actually here, you see that the change in entropy is negative because we consider a gas as an open system. Good. But if we consider the gas and the reservoir together, then we will have a closed system. Remember what is a closed system? I explained you in the very first slide, right? Closed system. Open system, isolated system, and closed system. If you do not remember, please, yeah, take a look at it. Good. So we know that in a closed system, the entropy of the system increases or remain constant, but it never decreases. And this is the second law of thermodynamics. Yeah. Now we go to some very famous applications of the second law of thermodynamics, but maybe I propose a break of also 5 to 10 minutes. After that, we will consider together the two applications of the entropy. Will be the last part of the lecture. Good. Please turn on the camera and we continue. So we consider here a very famous application of entropy in our real world, the heat engine, or more simply the engine. Bạn nào còn mic tắt hộ tôi phát. So when we talk about the heat engine, we talk about a device that extracts energy from the environment in the form of heat to do work, right? We extract energy in the form of heat to do work for the car, for the motorcycle to move. So at the heart of every engine, we have what we call a working substance. A working substance. For example, in your motorbike, the working substance is the gasoline, for example, a mixture of gasoline and air. Good. If an engine is to do work on the sustained basis, then the working substance must operate in a what we call cycle, such as the cycle that we see in the PV diagram. And the working substance must pass through a closed series of thermodynamic process we call strokes, right? So in strokes, for example, we have 2-stroke engine, 4-stroke engines. You should heard about it. The working substance will change the states from one stroke to another and then return to the initial stroke. So we finish one cycle, right? Here, I give you an example here of a steam engine. So the first engine, very efficient engine that changes the world completely. So steam engine. So the working substance is water. This water is in both vapor and liquid form for the working substance. Nowadays, in our motorbike, we have an engine working with the substance of gasoline and air mixture. So these are several engines. Now, we will consider a specific engine, which is a Cardinal engine. So you know the Cardinal already. Now we will consider what's so-called the Cardinal engine. We will consider an ideal engine. So in an ideal engine, there's all the processes are reversible and there's no wasteful energy, right? No friction, no turbulence, and no dissipation of energy. And the Cardinal engine is actually the best at using energy as heat to do useful work. That's why we pay attention on the Cardinal engine. It set the limit of the efficiency of an engine. Yeah. Now, here is the schematic of a Cardinal engine. Tất cả các bạn đâu hết rồi nhỉ? Ở đây tôi thấy rất nhiều bạn không bật cam này, Tự Duy này, Tuấn Hưng, Đức Nguyên này. Các bạn không nghe thấy tôi nhắc à? So, when we look at the schematic of a Cardinal engine, what do we see? We will see 2 reservoirs here. So we call it here the hot reservoir, having the TH, the temperature TH, and here the cold reservoir having the temperature TL. The heat is transferred from the hot reservoir to the cold reservoir, and a certain amount of heat is used to do work. Okay. And if you see the loop here, suggests the working substance operating in the cycle. Very similar to what we see on the PV diagram. If you put the PV diagram here, you see that this is the cycle. So we have the heat, you have the work, and so on. Okay, because here the substance receives the heat from the hot reservoir, then the heat here is positive. The heat here is negative because it's lost from our system, from our gas, right? Yeah, this one is negative, this one is positive, this one is negative. Good. Of course, the work is done on something. For example, the work is done to move our wheels, to run our car, our motorcycle, and so on. And here, this is the PV diagram. Good. The PV diagram of our Cardinal Engine. What do we have? We have an isothermal expansion connected with an adiabatic expansion connected with an isothermal compression, and then an adiabatic compression. So this is the PV diagram of the Cardinal engine. Two isothermal processes connected together by two adiabatic processes. Please remember, for isothermal processes, we have no change in temperature, while for adiabatic processes, we have no change in heat. Good. Yeah, this is the explanation. What do we have else? Now, yeah, this one. This thing I already explained, okay? What we need to pay attention is the work done by the Cardinal engine, because this is what we need for an engine, right? The work. For a closed cycle, we know that the net work done by the cycle equal the net heat provided to the cycle, right? This is the first law, and we apply for our Cardinal engine for a closed cycle. Then the work can be written as this one. This is the work done for the Cardinal cycle, right? Because we received the heat here, we lost the heat here, so the work, net work equal to the net heat, and this should be this one. Đàm Lâm, will you agree with me? Bạn Đàm Lâm. Dạ. Tôi đang nói tới cái phần nào rồi nhỉ? Tôi đang nói tới cái gì?
Trở lại mà. Tại vì là loa của em nó hơi có vấn đề, là em
không có giải
hết.
Không có giải thích. Tôi ghét nhất là mấy bạn đã không tập trung còn đi giải thích. This is for the work, okay? How about the entropy change? How about the entropy change of a Cardinal engine? So we see that in a Cardinal engine, there are only two reversible and neutral transfers as heat, right? Because in the adiabatic process, there's no transfers of heat already. So the two changes in the entropy of the working substance will have one at the temperature TH here and one at the temperature TL. Then the entropy change in the final form should be written then this one. This is the entropy change in the hot reservoir. This is the entropy change with the minus in the cold reservoir. You agree with me? And because for a complete cycle, we also have change in entropy equals 0. Good. You agree with me here? Then we should rewrite like this. But what do we see? We see that the temperature of the hot reservoir is higher than the temperature of the cold reservoir, right? Then we should have the heat received here should be higher than this heat lost here. So more energy is extracted from the heat as heat from the high temperature reservoir. So the hot reservoir, then it's delivered to the low temperature reservoir or the cold reservoir. Good. Then what we really pay attention for an engine is the efficiency, right, of the engine. We want to know the efficiency, hiệu suất of an engine. We can calculate the efficiency of anything as the energy that we get and the energy that we pay for. This holds for any engine. And in our case, this is actually, this formula. So this is the work, what we need, right? And this is what we need to pay for. So we need to extract this amount of heat, and this is the work that we need. And finally, we have the expression of the efficiency for the Cardinal engine. So here is one expression, and here is one expression. The efficiency of a Cardinal engine. Is it okay? I take a break of 10 seconds here for you to read. So this is the work. And we rewrite in this form. Or, in this form. It's still similar. Good. Later on, we will see that no real engine can have a thermal efficiency greater than Cardinal engine. In the next part, I will prove it. Yeah, this is a statement, and then I will prove that this statement is true. Now we consider another engine, the Stirling engine. The Stirling engine, actually it is developed also very long ago, 1816, but we still use it until now in automobiles, in spacecraft, in military submarines, because these engines are more quieter than others. So we still apply it. And in our Stirling engine, we have the two isothermal processes connected with two isochoric processes. Two isothermal processes connected with two isochoric processes. Okay, and the heat is supplied here and here. Another heat is added here and lost here. Good. So this is the PV diagram. Now we do the same procedure to calculate the efficiency. The efficiency here is actually what we need. Is still the work. What we pay for is the Q prime H here. So this is actually the sum of the two things here, QH and Q. Yep. So when we rewrite it, we just replace the QH, the Q prime L and Q prime H as this one. Yeah. So the QL here is actually one part here, and one part here is the lost. Okay. Here also the QH here, and one part is lost for this. So the QH cannot, is lost a small amount here, and QL is also lost a small amount here. Then when we calculate the efficiency, it will take this form. And when we see here, we compare with the Cardinal efficiency, we see that the efficiency efficiency of the Stirling engine is also smaller, yeah, smaller than the Cardinal engine. Here I have an exercise. So for us to understand better the the Cardinal engine, I will move on, okay? Here, what we need to find is the efficiency of this Cardinal engine. We know the working temperatures. We know that the engine performs a 1,200 joules of work each cycle, okay? And each cycle will take 0.25 seconds. Firstly, efficiency of this engine. Secondly, the average power of this engine. Then the heat extracted from the hot reservoir delivered to the cold reservoir, and then the entropy of the system. How to calculate it? Maybe. How do we calculate it? Good. Then we apply the formula for the efficiency of this Cardinal engine. This one. So we have the efficiency of around 65%. This is for the efficiency. For the average power, so we know the power is the work divided by the time. So for each cycle, we know the time already. Then we calculate the average power of this engine. So it is around 4.8 kilowatts. If we want to calculate the QH, so the hot reservoir provided to the system, then we also start from the formula of efficiency, because the efficiency is the ratio between the work and the hot reservoir, heat of the hot reservoir. Then we calculate the heat. Okay. Then the cold reservoir, we also know. When we know the heat of the hot reservoir, the work, we should be able to calculate the heat delivered to the cold reservoir. And finally, the entropy. The entropy. Good. We know that this is a closed system, reversible process, because our gas can restore, right? Can restore to its initial states. Then we should have a change in the entropy for the whole process equals 0. But for the process, for the entropy change at the hot reservoir and at the cold reservoir, we should have this one. Good. Now we continue to see the refrigerator. We consider a perfect refrigerator. I'm sorry, not perfect. We consider our ideal gas working in a refrigerator. Then, if we consider an ideal refrigerator, I mean there's no wasteful energy. Okay. So the refrigerator will operate as a Cardinal engine, but reversely. It means that this time we will provide the work for our system to transfer the heat from the cold reservoir to the hot reservoir, because what we need is to use the space of the cold reservoir, right? Then we do inversely. Now we do not create work, but we provide work. We do not transfer the heat from the hot reservoir to the cold reservoir, but we transfer the heat from the cold reservoir to the hot reservoir. So this is a refrigerator. Then what we want is to see the efficiency of this refrigerator. But for a refrigerator, we call it the coefficient of performance. Okay. For the engine, we call it the efficiency. For the refrigerator, we call it the coefficient of performance. Good. This is still also the same. What we want is the heat to be extracted from the cold reservoir. And what we need to pay for is actually the work. Right? This one we need to transfer a certain amount of heat from the cold reservoir here. Yeah, and what we need to pay for to do it is the work. Then I can establish the expressions to calculate the coefficient of performance as this one and this one. Okay. So this is the way you calculate the coefficient of performance of the refrigerator. Please remember it. Good. Now we consider the efficiency of real engines, any real engines. I said previously that the Cardinal Engine will have the biggest efficiency. And here we prove that no real engine can have an efficiency greater than the Cardinal Engine. So the Cardinal Engine will set the limits for any type of engine. We know that every type of engine cannot go beyond the efficiency of a Cardinal Engine. So if it could, the engine would violate the second law of thermodynamics. And how to do so? We assume that we have an engine X. This is our assumption. And this engine X has a bigger efficiency. This is our claim, okay? And the purpose is that we prove that this claim is wrong. Now, what we do is that we couple our engine, this one engine X, to a refrigerator, this one. Then we adjust the Cardinal refrigerator stroke so that the work it requires per cycle is exactly equal to that provided by our engine, this one. So what we have here is the work of the Cardinal refrigerator equal to the work provided by our engine in magnitude, về độ lớn đó. Then there's no external work is performed on or by the system of engine and refrigerator. So you understand? We couple this one and this one. What to do? If our claim is true, then this one should be bigger than this one, right? Here, this is the efficiency of the X engine, right? And it should be bigger than this one. This one is the Cardinal Engine. You agree with me? Then we should have the QH bigger than Q prime H here. This one is bigger than this one. Good. And because the work of the two things here is equal, from the first law, we can rewrite here. This one is the work of the Cardinal engine. This one is the work of the X engine. We rewrite it. We should have this one equal this one. And because we know that this one is positive, okay, QH greater than Q prime H. So this one is positive. We call this amount Q, and this one is bigger than 0. Good. Do you understand until here? I hope so. Nothing hard to understand, right? We continue. Then we will have this amount Q here, and it should be bigger than 0. This is actually the heat that is removed from the cold reservoir and transferred to the hot reservoir, and it requires no heat. I'm sorry, it requires no work at all. Okay, we have this amount of heat. If we have this claim, and because we do not need to provide more work to our refrigerator, so our refrigerator can work as a perfect refrigerator. Our system here, the engine coupled with the Cardinal refrigerator, can work with a perfect refrigerator. So a perfect refrigerator in a perfect refrigerator, we do not need work to transfer the heat from the cold reservoir to the hot reservoir. So this is the equivalence of our system. Then, what is wrong? If we consider the entropy of our perfect refrigerator, okay, the entropy does not change for a complete cycle. The entropy of our refrigerator does not change. But the entropy of the two reservoirs, of course, will change. So we can calculate it easily from the change in the cold reservoir and the change in the hot reservoir. It will change. Then the entropy change for the entire system, we can write it like this, right? And if we put 0 for delta S, I'm sorry, here we do not even put 0. Here, when we want to consider is that because the heat from the hot reservoir is higher than the heat from the cold reservoir, then if we replace any value here, we should have a change in entropy that is negative. So this goes against the second law, right? Then this is really a violation of the second law. So we know that our perfect refrigerator, what we propose here, does not exist at all. This also means that our claim from the very beginning, having an engine X with a higher efficiency of a Cardinal engine, is wrong. So our assumption is wrong. Then we can prove already that no real engine can have an efficiency greater than that of a Cardinal engine when both engines work between the same two temperatures. Okay. So, do you have any questions? If not, we summarize. For this part, we see the reversible and irreversible process. And we understand that around us, there are mostly irreversible processes. And we have a way to explain why an irreversible processes will have to go in one direction and not another direction, right? By the use of the definition of entropy. And to define entropy, we also have two ways, two approaches to define entropy. The first way, this is the microscopic approach. We define the entropy as the number of microstates that a system can take on. The second way to define entropy is the relationship between the heat added to the system per the unit of temperature of the system. Then we find a way to calculate the entropy change of our system, right? Please remember that for an irreversible process, we should find a reversible process that connects the same initial and final state. And then we calculate the change in entropy for this reversible process. And this change in entropy will also equal to the change in entropy for the irreversible process. Now, the second law of thermodynamics, and you also should remember that this holds only for a closed cycle. For a closed cycle, the entropy equals 0 if the process is reversible and always bigger than 0 if this is an irreversible process. Good. Then we studied the engine, the Cardinal engine, the efficiency of any engine, the Cardinal refrigerator, and the efficiency of any refrigerator. And this part will be surely happen in the exam, in the final exam. This week, maybe next week, at the beginning of next week, I will set a midterm exam, a very short midterm exam for you. And the midterm exam will be easy for you to gain points. But the final exam will be harder for sure. It's always like that. Because in the final exam, we summarize everything you learn. But in the midterm exam, I will limit it in the two first part, the kinetic theory of gases, and the first law only, and less questions also. Is it clear? Any questions?
So just two first part, right?
Just two.
And after the TET holiday, we will have a lot of exams. So please pay attention. Do the revision from now on. Yeah, not just wait until the end of the days. Okay. Then if there's no questions anymore, we stop here. Thank you so much for today.
Teacher, I have a question.
Yes.
The content of the midterm exam is about chapter 1 and 2.
I just said. Tôi vừa mới nói xong nhé.
Em xin lỗi, nghe em rõ.
Phần 1 và 2. Chúng ta có 4 buổi với nhau đúng không? Thế thì cái phần 1 là cái gì? First law, phần 2 là kinetic theory of gas. Nhé. Các bạn tập trung vào đó và câu hỏi nó cũng sẽ dễ thôi nếu như mà các bạn nắm được cái. Tuy nhiên thời gian là hạn chế. Okay, thank you. So see you in some of you in the tutorial part.